Welcome to another example. In this example, we're going to look at air in a piston cylinder, and we're told the pressure at state 1 is 10 pounds force per inch squared, and the temperature at state 1 is 500 degrees Rankine. And we're told the final volume is 1 cubic foot, and the process is described as PV to the 1.25 equals a constant. So this is a polytropic process. And we're told the mass of the air is 5 pounds mass, and that we can assume it is an ideal gas. So I'll draw the picture for you. So I just draw a control volume around my piston cylinder system. And I'm going to write down air, but I'm going to also make a note here that it's ideal. That'll help us remind us how to figure out the different properties. We have a couple goals. We're asked to determine the heat transfer, assuming C sub P is constant. So this is part A. And then for part B, we're asked to determine the work and heat transfer, assuming data from table A22E. And then we're supposed to sort of compare the two methods. So we'll walk through this process twice with different property lookups. So a good way to start a problem is almost always to write the first law for it. So the change in internal energy plus the change in kinetic energy plus change in potential energy is equal to Q minus work. And this is for process 1 to 2 because we only have 2 states in it. And we might assume that kinetic and potential energy are 0. And we were actually asked to solve for both Q and work, so it would be a bit of a stretch to cancel either of those out. So we're going to end up needing to solve for the change in internal energy, where we find out mass times U2 minus U1. And it looks like we'll be using 2 different methods to check that. We're going to need one other piece of information to close this. And probably what makes sense in this case is to use the polytropic process that we had. So we were told this was a polytropic process, so we could probably integrate PDV between 1 and 2 to solve for this. And if we remember that for a polytropic process not equal to 1, we actually have an equation for that. So you could actually do the integral, or you can just look this up in your textbook. Work from 1 to 2 is going to be the mass times pressure 2, specific volume 2, minus pressure 1, specific volume 1, over 1 minus n. And n is known. In this case, they told us it was 1.25. So that is known. We're also given the pressure at state 1. And we have volume at state 2, which will allow us to get specific volume at state 2. So we have enough information to get 2 of those. We were also given the mass of the system. So we have that piece of information. And we're going to need to look at property relationships to figure out the rest of this. One of the property relationships we can use, because they told us to treat it as an ideal gas, is we have 2 different versions of the ideal gas law we can write. PV equals to RT equals RT at state 1. And we can also do the same thing at state 2. And it probably makes the most sense to do this at state 1, because at state 1 we have pressure 1 and we have temperature 1. So that would allow us to solve for V1. So that's kind of great, because that was one of the missing things that we had over here. And then we could either use the ideal gas law again, or we can use the polytropic relationship. So we also know that P1 V1 to the 1.25 is equal to P2 V2 to the 1.25. And in this case, we now know V2, pressure 1 was given, and we could use the ideal gas law to solve for V1. which would give us our last pressure. So it kind of allows us to work through the problem in a little bit more expedient way. And then, of course, we need to solve for the change in internal energy. And they asked us to approach internal energy in two ways. For part A, they said you should use the fact that specific heat is constant, which means we can use this approximation, delta U equals C sub V delta T. And we can look up the C sub V values based on knowns. We don't actually have T2 yet, so we'd have to use one of our other relationships to get that. For part two, we're going to use the table. So internal energy at state 2 is a function of T2. Internal energy at state 1 is a function of T1. And this is going to come from A22E. So I've advocated for making a table that sort of summarizes all the state information. If we did this for this problem, it kind of is useful to make a note of what we know and don't know. So we know 10 psi is the pressure at state 1. We know the temperature is 500 degrees Rankine. And we know that the way we get between the two states is polytropic. And then at state 2, we know the volume. And we also know the mass. So the mass is constant, and that's 0.5 pounds mass, and that would go between the two. So to actually kind of include some of the things we're looking for, we need internal energy at state 1 and internal energy at state 2 in order to calculate the internal energy change for the system. And we have two different ways we can do that. And then we have volumes. We need specific volume to do the work calculation. So we need specific volume at state 1, and we need specific volume at state 2. And of course, that'll be closely tied to the actual volume. So that's probably the easy one to get. So we'll just sort of stop here with our state diagram and start calculating as many things as we can based on our polytropic process and the ideal gas law. So the first property calculation that's probably the easiest is to solve for specific volume at state 2. We're just going to divide the volume divided by the mass. So this is going to give us 2 cubic feet per pound mass at state 2. So now that volume is known. And then we also wanted to calculate specific volume at 1. We could do that using the ideal gas law because we knew the universal gas constant, temperature 1, and pressure 1. So this is a nice way to sort of think about this. The universal gas constant in English units is 1545 foot-pounds force per units of kmol. And if we did want to actually just remove that, we can look up the molecular weight of air, and it's 28.97. And this will put it in pounds mass degrees Rankine. So there's a pound mole conversion that we kind of did on the fly there. And then we'll put in 500 degrees Rankine because that's our temperature. And then of course we'll have to do a little conversion for our pressure. We were actually told the pressure in PSI. So we have 10 times 144 pounds force foot squared. So that'll get us into feet squared from inches squared. And the pounds force will cancel, and we'll have cubic feet per pounds mass. So specific volume at state 1 is equal to 18.52 cubic feet per pounds mass. For the polytropic process, that tells us a little bit of sort of useful information. We know that the relationship P1, V1 to the 1.25 is equal to P2, V2 to the 1.25. And we have specific volume 2 now. We have pressure 1 and specific volume 1 now. which allows us to solve for pressure 2. And the reason we want pressure 2 is it's the last piece of information before we could use the ideal gas law again to solve for temperature 2. So we can do a little bit of algebra here, and pressure 2 is going to be equal to V1 over V2 to the N times P1. And we put numbers in here, we're going to have 18.52 over 2. Both of those are in cubic feet per pound's mass. So that'll cancel. I will raise that to the 1.25. That was the N we were given. And we'll multiply that by 10 pounds force per inch squared. So our units are going to be pounds force per inch squared. And we find that pressure 2 is 161.5 pounds force per inch squared. So I'm going to go back to my collection of state information, and I'm just going to update this table. I already added specific volume at state 1 and specific volume at state 2. And the last thing I found was the pressure at state 2, which we just found to be 161.5, and that was in pounds force per inches squared. So the last thing we really need to do to figure out all the information in the system is we need to solve for temperature 2. So we're going to use the ideal gas law again, this time at state 2, where pressure 2, specific volume 2, and the ideal gas constant are known, which will allow us to get temperature 2. So pressure 2 is 161.5 pounds force per inch squared. But we really want that in feet, so we'll multiply this by 144 inches squared per feet squared. And then we'll insert the volume, 2 cubic feet per pound's mass. And that'll get rid of almost all the feet. And then we need to use the ideal gas constant, 1545 foot-pounds force. And of course, to get rid of the moles, or the pounds moles, we'll put 28.97, which is the molecular weight, pounds mass, degrees Rankine. And that'll cancel pounds force and pounds mass both. And we'll end up with that last foot canceling, and we'll end up with degrees Rankine. When you do this calculation, you get 872 degrees Rankine. And we need this information to go look up internal energy at state 1 and state 2 in the tables, particularly when we're doing the A22 lookup. So we just solved for temperature 2, which we found to be 872 degrees Rankine. So we found everything that we could possibly need in the table except for the 2 internal energies. And of course, remember that we're going to use 2 different methods here. For part A, we're going to use delta U equals C sub V delta T. So we're going to need the temperature either way. But we also were asked to solve for U2 and U1 using table A22E. And so we can now do that lookup based on only temperature. So if you turn to A22E, you can find this out pretty quickly. We find that at state 1, we have 85.2 BTU per pound's mass. And at state 2, we have 149.6 BTU per pound's mass. And the very last thing we might do is look up C sub V at the average temperature. And we can get this out of A20E. So in A20E, we looked this up at 500 degrees Rankine. So you could do the average, or you could use this value. In this case, this was the value that made sense to use based on the way the constraints in the table. So now we're going to do the calculations for the different variables. Way back in the beginning, we determined that for a polytropic process, our work from 1 to 2 is going to be the mass times pressure 2, volume 2, minus pressure 1, volume 1, all over 1 minus n. And we have carefully solved for each of these values. So we can now calculate this work term. So we have 0.5 pounds mass. And then we have 161.5 times 144 times 2 minus 10 times 144 times 18.52. And that is all over 1 minus 1.25. And the units on this are kind of funny. This will be pounds force per foot squared because we did the conversion to feet from feet to inches already. And then our specific volume was in cubic feet per pounds mass. And then in order to get this to BTU, we actually need to do one last conversion. 1 BTU is 778 foot-pounds force. And that cancels the last of the cubic feet. And it also cancels the pounds force, pounds mass cancels over here. And we should be left with just the value, which is negative 51.0 BTU. And this isn't going to change with either method A or B. So the work term, because it depended only on pressure and volume, isn't going to actually change. But our heat transfer term will based on the internal energy. So now the calculation that we're going to do is basically Q1 to 2 is equal to work 1 to 2 plus mass U2 minus U1. And we're going to change this part of the equation for part A and part B. So for part A, this was the part where we assumed constant specific heat, delta U equals C sub V delta T, and we looked up C sub V. So we can calculate this. U2 minus U1 is equal to 0.171 BTU per pounds mass, degrees Rankine. And this was the specific heat that we looked up in the back of the book. And then 872 minus 500 degrees Rankine, and that should give us BTU per pounds mass. So this is 63.612 BTU per pounds mass. And then we'll put this back into the first law to calculate part A. So we had Q1 to 2 equals work 1 to 2 plus mass times U2 minus U1. So here we'll have negative 51 BTU plus 0.5 pounds mass times 63.612 BTU per pounds mass. And this gives us a heat transfer of negative 19.2 BTU. So this is part A. And then we need to repeat the same calculation with a different internal energy calculation. So in part B, we were asked to calculate U2 minus U1 just from the table lookups, and we actually already did these table lookups. We had 85.2 minus 149.6 BTU per pound mass, which gives us 64.4 BTU per pound mass. So this is just a tiny little bit different than what we got for part A. And so we can put this into the same calculation where the heat transfer is work plus mass times U2 minus U1. And here we'll have negative 51 BTU because that was our work, plus 0.5 pounds mass, and then 64.4 BTU per pounds mass, and we get negative 18.8 BTU. So this is just ever so slightly different for part B using the table lookups instead of the constant specific heat. We probably could have made the constant specific heat calculation a little bit more accurate Because remember we assumed a constant specific heat at one temperature. It probably wasn't a great assumption. This is probably the more accurate calculation here. Just because we looked up everything at its specific temperature in the table. But it gives you a nice way to sort of compare two different ways to calculate internal energy for ideal gases.